Hey everybody, this is Mrs. Hilt, and in this mini lecture, I'm going to go over specific heat calculations. I'm going to quickly review what specific heat is, and that is the energy required at constant pressure to raise the temperature of 1 gram of any substance by 1 degree Celsius. And specific heats are different for different materials, and it does actually depend on the state of the material as well. So specific heat is similar to density in the sense that it varies based on the state. For example, we have liquid water, ice, and water vapor or steam all have different specific heats. They also have different densities. The reason why is because each of those substances, their particles are moving at different rates. Therefore, it takes a different amount of energy to increase their temperatures. And other parts of the equation or other things that we need to consider when we are performing calculations with specific heat are, well, heat or energy, mass, so the quantity of the substance that's present, and then the temperature change that the substance went through. Now, here is the equation, and you will, at different points, solve for different variables. We'll start off by solving an example with Q, then we'll do a specific heat, and then we'll solve for temperature. Here are the units associated. Q is in joules, mass in grams, change in temperature is in degrees Celsius, and in order to end with joules, our specific heat units are joules over grams times degrees Celsius. So that means when you are multiplying the mass by the specific heat, the grams cancels out since grams is in the denominator of specific heat. And when you multiply temperature by specific heat, you are canceling out degrees Celsius because it is also in the denominator of specific heat. All right, first example. And as I'm going through this, I'm going to highlight our different variables so that, or in the same color so that they match up with the equation. Suppose you find a copper penny in the snow. How much heat is absorbed by the penny as it warms from the temperature of the snow, which is 8 degrees Celsius, to the temperature of your body, 37 degrees Celsius. And we will assume the penny is made of pure copper and has a mass of 3.10 grams. All right. So we have mass of 3.10 grams. We have the change in temperature, or at least we have the initial and then the final, so we can find the change in temperature by subtracting those, and specifically subtracting the initial from the final. And we do have specific heat because we know what the substance is. The only time that you will not know the specific heat is if you're solving for it. Sometimes it might be hidden, kind of like in this example where it really just told you the substance and that didn't exactly give you the value of the specific heat of copper. So we are going to have to go back to the previous slide and see what that is. All right, let's look at the table. And here we have copper at 0.38 joules per gram degree Celsius. So we're going to pull that and use that for our specific heat. All right, I'm going to flip to the next slide. All right, so I'll walk you guys through my calculations. Over here, I have everything set up, and there's one little change that I really should make. And that is with the temperature, because we do always want to make sure that we keep the correct number of significant figures, and I did not represent that initially correctly. 0 degrees Celsius, there we go. All right, so when you're solving for Q, the calculation is very straightforward, multiplying everything. And again, we can see how the units cancel out, grams, degrees Celsius. When you multiply those three numbers together, you'll get an unrounded answer of 53.01, and the units is joules because that's the only one that's left. Now we have to round it to 3 significant figures. And the reason why it's not 2, because the specific heat does have 2 sig figs. 3.10 has 3. 45.0 has 3. But the reason why we don't round it to 2 sig figs is because the specific heat is a constant. Okay, so we had to look this up. This is a known value, and we never base the number of significant figures off of constants. Okay, so we only base it off of the given values in our problem. So that is why this one is 3 sig figs. All right, let's try another one. Okay, the temperature of a 95.4 gram piece of unknown metal increases from 25 degrees Celsius to 48 degrees Celsius when it absorbs 849 joules of heat. Use this information to determine the specific heat capacity and identify the metal. So this is a 2-part question. We want to determine the specific heat, and then we need to identify the metal. Okay. So, first step, and as I'm walking through this one, I'm not going to be changing colors because that will just take forever. I do have everything color-coded on the next slide, though. All right, so mass is 95.4 grams. C, that's what we're solving for. Then our change in temperature is equal to the final temperature minus the initial. And our initial temperature is 25 degrees Celsius. And don't want to forget that 0. And we'll subtract that from 48 degrees Celsius. So you do need to pay attention on what direction it's going. So from 25 to 48, therefore it's ending at 48. And that means that our change in temp is 23.0 degrees Celsius. And since we know our Q, we'll write that in here as well. 849 joules. Okay. Now, our equation, let's write that down. Q is equal to mc delta T. Since we are solving for C, I'm going to rearrange this so C is all by itself and then plug my values in. If you're more comfortable plugging in your values and then solving, that's totally fine. Just make sure to show all of your work with whatever method you do. So Q over mass delta T is equal to C. Now I'm going to show you guys a little shortcut that we could have used for this, and that is by using the units to our advantage. So specific heat's units are always joules per gram degrees Celsius. It could be kilojoules, it could be kilograms, so there could be other variants, but it's always joules, or the energy heat unit, a mass unit, and a temperature unit. And how we could use this for our advantage with rearranging the equation is because if we're solving for C and these are the units for C, that means that we need to have whatever our joules is on top, and that's Q. Then we need to have whatever our grams is on the bottom times by whatever our degrees Celsius is, so our mass and our temperature. So that could have been a little shortcut if you are ever solving for C. Let's plug in those values now. 849 joules. We're going to divide that by 95.4 grams times 23.0 degrees Celsius. All right. I'll plug that in, and I'm actually going to switch to the next slide because that's where my answer is. Okay, so it looks just a tad bit different since it's all color-coded. This is where we left off. And once you type that in, you will get 0.387 joules per gram degree Celsius. And looks like I did make that temperature error one more time. Forgot to include that 0.0, which that is important because that would determine a different number of significant figures, right? And the reason why we have to record that 0 there, I know it seems silly, but whatever tool was used to measure the temperature could read that far. So we have to record everything that the measurement tool can read. And how I knew to make sure that the answer went to that decimal place is because both of the initial and final temperatures went to the tenths place value. Therefore, my final answer had to go to the tenths place value. So it needed to be the same level of precision as the least precise measurement. Since they're both the same, that means our final answer will be in the same place value as well. All right, and then the last step of this, identifying the metal. Now that we have the specific heat, how we identify the metal is by looking back at the specific heat table a couple of slides ago. So I'm going to flip to that. And it just so happened that it ended up being copper again. And you guys will never need to memorize this whole table. If you guys are ever asked to do a question like any of the last two that we've solved, you'll be provided either the specific heat within the problem, or you'll be given a table that you will need to reference. All right, on to our last example. Okay, so a 55-gram piece of aluminum, initially at 27.5 degrees Celsius, absorbs 725 joules of heat. What is the final temperature of the aluminum? And it does give us its specific heat, so we don't have to flip back to that other slide. Okay, so calculations with temperature can sometimes be a little confusing for students. So, and I think the reason why is because in the equation, we have Q equals MC delta T. And we're not going to end with the delta T. We know the initial. We want to know the final. So what you guys need to do in situations like this is first solve for the change in temp. Then you will use delta T equals TF minus TI to find unknown temp. Okay. So in this case, since we are solving for the final temperature, I will rearrange the equation. So delta T is equal to TF minus TI. So add TI to both sides. So delta T plus TI is equal to the final temp. All right, so this is step 1. This is step 2. Move those to the side and we'll go through the calculation. Actually, I'll flip to the next page since it's all drawn out. All right, so let's go over here. So I decided to rearrange the equation, and again, if you like to plug in and then rearrange, that's totally fine. Just be careful about that. Make sure you are not plugging in the initial temperature into this first step. So rearrange it by dividing each side by mass and specific heat. So Q divided by mass and specific heat is equal to the delta T. Now solving this out and seeing how the units cancel, we'll look at the denominator first. So since these two are being multiplied, the grams cancels out because that's in the denominator of specific heat. The joules is in the numerator of specific heat, so it's in the regular denominator, so joules cancels out. And since degrees Celsius is in the double denominator, so the denominator of the denominator, that ends up putting it up to the numerator. So that's how we end with a degree Celsius. So this is the answer for the first step. Then the second step, I took the change in temp, added it to the initial temp, and our final temperature is 42.1 degrees Celsius. It has 3 significant figures because the mass has 3 significant figures, the heat and the initial temp all have 3 sig figs, therefore my final answer will all have 3 sig figs. It just so happened the specific heat also had 3 significant figures. That was just a coincidence in this case. All right, if you guys have any questions or need any help, please let me know. Thanks for watching.